Today I want to talk about the Fermi's golden rule, the relation between the probability amplitudes from the time-dependent perturbations and the decay light through the cross sections. This Fermi golden rule is very important in the particle physics to obtain the observable quantity, which is the decay light, as functions of energy with angular distributions. Also, we can observe the cross section in the scattering phenomena. We were studying the Hamiltonians of the perturbing Hamiltonian in perturbation theories of quantum mechanics. We can write sort of the quantum size sort of wave functions in the basis of the positions and the time, and there will be some of the time phase factors that will be multiplied, and the coefficients will be also time dependent. That's the most general descriptions of the wave functions in space-time. And such is the wave functions satisfy the time dependence Schrodinger equations, the Lorentz equations. And if we insert sort of the psi such wave functions, then there will be some derivative terms of the time dependent coefficients. And some such terms comes from the exponential factors of the time evolutions of light. And there will be some HGO's terms, and such terms will be disappears in the both sides, and we can define the differential equation for the time-dependent coefficients. That is related with the perturbing Hamiltonian part, and some phase factors with the initial energy and binary energy. And the solutions can be written like that because that's just the integrations of the right-hand side with the time. Because such time-dependent coefficients, such coefficients of the wave functions we can term states mean the probability and amplitudes. So if we scale the such coefficients, we can define the probability. And using of the Fourier transformations and the standard functions, then such exponential factors of the initials and binary energy becomes the delta functions, and it means that the energy should be conserved in the initial and binary side. And we can define the decay light. Decay light is from the initial state to the final state. Such a capital gamma is the transitions, which is some broadcast of the binary and initial states on the perturbing Hamiltonian part. And there will be some of the phase space factors will be appears, which is some of the functions of the energy conservation and the number of the possible states of the binary and initial states. So that's the decay light. So the point is the decay light is proportional to the scales of the probability amplitudes of the perturbing Hamiltonian. And we know that the phase space can be written like that in the statistical physics. There will be some three-dimensional position space and three-dimensional momentum space because they are the canonical conjugate. And we not consider that the position space that is just equal to the V over the device cube, and we can relate the such momentum space in terms of the spherical coordinate. And because we want to introduce some of the relativistic versions of the such Fermi golden rules, and the Lorentz invariant phase space LIPS is these three P's momentums over the E is invariant under the Lorentz transformations, even the P primes and the E prime. So we will introduce the additional Lorentz invariance factor to E. I still the all phase-based momentum space differential. So we can relate to the decay light, the parameter rules with full terms of the Lorentz invariance space. So the capital gamma from the initial state to the final state is a 2E factor. Particle 1 decay to the 2 plus 3 both and central. And there will be some probability amplitude. It can be obtained in the Feynman diagrams, which is come from the time-dependent perturbation. It describes the quantum theory, and we will multiply the phase-space terms such as some Lorentz invariance factors multiplied together, and there will be the full momentum conservation terms will be still here. So that is a parametric golden rules of the decay light. And we know that there is some relation between the decay light and closed auctions. Using of dimension analysis, decay light is over the time. And there is a number density, 1 over the x cube, because the number is just the no dimensions and the volume is the x 3 dimensions, and the cross sections as the dimensions area, and the velocities that are x over the t. So that was just constant that capital gamma is equal to the number densities cross section velocities multiplication. So cross section can be written as a master of the B1 sort of B2. We will recognize the number density here because we will consider that just one two particles that scatter, so number density is just equal to the ones, and there will be some outgoing particles 3 plus 4 plus and etc. And we can write the cross sections from Gauss rule, and there will be some additional factors to be appear. We will discuss it in the next term of these factors, such as E12 and some V1, V2, such a term. That is just coming from that such a relation between the decay light and the cross sections. There will be some of the velocity tends to be appears in the denominator. And there are some of the probability amplitudes, and there are the pace stem, and some of the Bowman semiconduction. So there are some of the parametric order particle structure. Such as the probability amplitudes can be obtained by the matrix corresponding to the Bowman diagrams. It discussed in contemporary theories and the previous scales and the integrals of such a pace, especially Lorentz invariant pace factor. Then we can obtain sort of the total cross section of the decay light, and also we can obtain the functions of the energy or functions of the some other distribution and the regular distribution, and we can obtain the various informations, for example, Higgs probability decays and the various particle phenomena. So such a decay light and cross sections are important to the observable quantity in the particle physics, and that's important rules between the observable quantities and the Bowman diagram.